Award-winning entrepreneur, inventor, patented author. You've done a lot of cool stuff in your time, and I'd really like to chat about some of your ideas moving forward. In the last email, we discussed, well, you discussed your ideas on cooperative living and how tying in point of use separation technologies is a real key to this regenerative future and decentralizing of grid functionality. So welcome to the show. Thank you so much for being here, and let's get into it. Please tell me a little bit about cooperatives. Do you want to start there?
The cooperatives is a good idea to start. We could talk about the history or whatever. That's very interesting. It was very educational. I don't think everybody should go through it, but anyway, there's a lot of interesting points in it. But what I've come to the realization in talking to almost anybody and everybody, the problem of the world is money. You can talk about a whole bunch of things and whatever else like that, but when it comes down to it, everybody's working their tail off for money. And it's survival, and it's this money, and well, why do we need so much money? Okay. So this is what Buckminster Fuller talked about back when I read about this stuff in the 70s, where he talked about, and I didn't get it back then, but he called the productive dwelling machine. And so I'm going, oh yeah, that's really nice, I understand. And he's saying, yes, if we had a productive society based upon the individual units being productive instead of consumptive, this would be able to change the economy. So according to what I've read, Thomas Malthus about the Malthusian theory about enough to go around, and he explained that, well, that's not really right, because with technology you can do more with less. So all of that made a lot of sense, that all of this needs to be put together as a package. And this goes way back before the Romans or whoever got into this whole centralized idea, and it was based upon the technology that existed at that time. I mean, back then you carried a bucket of water from the river. Same as when I was in Alaska, people were carrying a bucket of water from the river. So the technology was the hindering factor. So when Buckminster Fuller invented the geodesic dome, I thought, man, this is great, because it logically does more with less, which is interesting to me, because I learned about domes, and I learned about septics, and I learned about composting, and I learned about gray water, and I learned about geothermal, and I learned about a whole bunch of different things. And they all started piecing together. And as I was in the wastewater business, I learned about plastics. And so when we first made our first composting tank, it was welded together with aluminum. Next ones were fiberglass. And then we went into rotational molding. I discovered that my technologies were not going to be able to be manufactured the way I wanted them to be before. And so this led me to be able to look at this recycling of this stuff. And so the first thing I got was a bunch of 55-gallon drums. But I had learned about ozone before, and so in order to make a living, I actually sold an ozone system for a swimming pool. The composter that I've designed now using this IBC tank, when I used to manufacture my tanks, it cost me a lot of money to make the molds. It cost time. I had to do it in one place. Now these IBC tanks are floating around everywhere. Okay, you can get them for 50, 75 bucks. So the whole invention now is just the engine on a car. And so it has automatic mixers, it's got automatic augers, it's got automatic sensors, screw conveyors it into a little bag, puts a twist tie on it. The composter, which is really the unique thing that I didn't understand before. In composting, you vent carbon dioxide and water vapor. And so we always said there's no odor because it's aerobic and it's wonderful. But people in Arizona asked me one time, where do you get the water? Good point. Okay, now they do get rain, but not a lot. And you can recycle the gray water. But if every time you flush the toilet and every time you pee and every time that water goes in the composter aerobically and vermiculturally, it's turned into water vapor. So it's not toilet to tap, as what the engineers try and sell in California and what the whole world is trying to do in what they call water reuse. I call water recycle. And water recycle means you use it 1,000,000 times. They're talking about water reuse, and they're talking about for flushing the toilet or irrigation. That's the best the engineers got now. Worldwide, because they've got a commingled source. A friend of mine said, the real problem in the world is that we are not taking care of our humanly bodily functions with respect. So it's 90% water. And in this composter, we can evaporate that water, chill it, and put it back into the beginning of the gray water system. So if you're out of water, you can go to the grocery store and buy some juice and drink it and pee. And we will convert that water, not we, but the worms and organisms. So it's not an engineering thing, this is a natural thing. Okay, back to the cooperative. In doing this dome and doing this water and doing this composting thing, I understand now what Buckminster Fuller talked about, the productive dwelling machine. My goal is to make a utility for the cooperatives. They already have a cooperative, the utility of electricity. They install solar panels. So they've already got decentralized electricity. There's no reason why they can't have decentralized water, sanitation, and if you put the whole package together for the productive dwelling machine, they will manufacture the recycled plastic geodesic dome and other configurations out of recycled materials locally using rotational molding or extrusion and making a fiberglass prototype to be able to show people. To move into the rotational takes some more money for the machinery. I have the prototypes, which we can actually show you today. The prototypes operating that are taking rainwater and converting it to potable water. And it's simply using ozone and reverse osmosis. Now, if you go to all the engineers and everybody in the world, they'll tell you that rainwater is impossible to make potable because of the PFAs supposedly in all of the clouds. Well, reverse osmosis takes care of everything. But it's ozone that's the secret. So ozone, which I've been working with about 20 years, is a fantastic thing. Wrapping this back into the cooperative. The cooperative can not only supply electricity, but they can also supply water from the air, or if you have a well and you've got bad water, ozone flocculates iron and manganese while killing everything, whereas chlorine does not kill everything, does not, especially in swimming pools, does not kill cryptosporidium. And ultraviolet light is a nice thing, but the wavelength disintegrates and the bulbs are made of mercury. Even the other bulbs that are the LEDs at the moment are expensive and they do not last. And so ozone is Mother Nature's secret about disinfection. But the main thing about it is this realization that human excrement and human pee is valuable. Okay, it's 90% water. So these sewage discharges around the world are one of the main problems, which the composter takes care of. Then you can get into the water thing. Then you can get into the housing thing. Once you decentralize and you put people in productive dwelling machines and you have productive communities, that's where the strength is. I believe that the power is in water. So to me, the power is in decentralization of water and the technology.
Let's put a quick pause on the cooperative, because I think that's a fascinating part, but just some background on the domes, maybe an overview of what septic tanks actually do and why your solution is better, and then maybe touching even on how ozone works. I mean, there's just so much here. Let's dig into it.
Okay, we'll start with a dome. Okay, so the dome encloses the most amount of volume with the least amount of surface area. So that's pretty basic stuff. And there's different kinds of domes, especially that they sell right now, which are called strut-up domes, and they got little plastic coverings, and it's called glamping. And they're doing a lot of business that way. There are what are called panelized domes, and that's what I've made in the past. But the panelized dome has a problem because there's so many joints and expansion and contraction and temperature, you have a whole bunch of leakage. And so I came up with an idea of a shingle panel effect. And so I made a little prototype in Alaska that was 12 feet and worked out with just the skin. But it was bolted together on the outside, which I didn't like the penetrations from the outside. So by making the frame on the inside, so you have panels that bolt together on the inside, but elapse on the outside. When you manufacture out of fiberglass, you have two parts. You have a bottom and a top. It's called the sandwich, and then you have to put them together. When you rotational mold it, it's all one part. When you make them out of fiberglass, you can make about 2 a day. When you make them out of rotational molding, you can make 1 an hour. Normal dome is like 75 panels. Comes to less than about $100 to $50 a panel, complete, that can be erected in less than 6 hours by 3 guys with scaffolding and rope. The real problem to me, I believe, in the school is the architects never talk to the engineers. The class should be architectural engineering. When you go to school, you don't go to school to become an architect and say, well, that's the other guy's problem. When you design a building, it should run itself, it should take care of itself. It shouldn't be a burden on society, it should be productive. So the first thing in the morning you wake up, what do? Well, it's right on business, okay? Now, the thing we've learned about with the whole toilet thing started was a long time ago. I mean, people used to just defecate. Then when it got to London or something like that, they had throw buckets out the window. And so then they came up with gutters, and then they came up with pipes to the river. But it was always get rid of this stuff because it stinks, and there was cholera and different things. So it was associated right away that it's disease causing. But there was no understanding that the possibility of composting in a vessel, which a guy by the name of Richard Lindström in 1947 invented in Sweden, this composting thing. So I got into the composting in the 70s with Abby Rockefeller, who bought the rights for Clevis Multrum. So that's where I learned about my composting thing. So in the 70s, I became a distributor, put one in my house, learned about it, sold some. And so then people said about gray water. Well, what are you going to do with the rest of the gray water? So I learned about sand filters. And so the first thing was sand filters. So I went through that experience. Then when I went to Alaska, I learned about aerobic from Northern Testing Laboratory. So I learned all these things from just working with people. So the real one of the issues to me is this realization that we can take the existing toilet system worldwide and cap it off and take that lines now become gray water lines. So if you take every toilet off and put a cap on it, all that plumbing is gray water. Then with vacuum flush toilets, like I said before, and there's different kinds, but I've used what's called Dometic Sealand, which from Ohio, that was a great person, great company. And the vacuum lines are 1.5 inches, and you can snake them up and down and over and out and everywhere you want to, over 100 feet. This is a puddle of water to flush. You've seen them where they have the foot-operated ones or whatever before on RVs. Well, they have these beautiful ceramic ones, and gorgeous. The whole toilet industry, the largest ones is called Toto in Japan, and they have these beautiful, and you take Bill Gates, who spent over $1 million reinventing the toilet, and send it to England, where these guys got a bunch of little screw conveyors and everything in a little toilet, and then they burn it. And so it's not recycling it, and there's a whole bunch of energy or whatever. If you just let Mother Nature take care of it in a box, but the box needs a little work. And so the thing about when you have this box, it needs to be able to mix, it needs to be able to remove it, it needs to have a water reservoir, it needs to be vented. So those are the things that I've kind of improved upon and now made it so it's automatic. When I was watching a Star Trek episode one time, they were talking to children on space. They asked the engineer, well, what do you do with the toilet stuff? And he said, oh, do I have to answer this? And he said, yeah, the captain's, you got to tell him. And I said, well, we have the biomatter resequencing converter. I thought, that's the name for it, composting toilet. Who wants a composting toilet? Everybody wants a biomatter resequencing converter. Sounds good to me. I understand. And all the other composting and everybody with the urine diversion and all that stuff is totally ridiculous. You need to get the stuff into a box that Mother Nature can take care of it the way that it's done just in nature, only you got it in a box so it's contained. And it all converts. And what's left are what are called hydrocarbons, and is the best soil you can possibly get. So the box is important. The gray water was interesting to learn about. The biggest part about gray water is organics, of course, and there's some bacteria and things. Working with aerobically, oxygen is a real good thing, and it builds bacteria, and so the stuff eats up the things. And I went through it. I had a 3-tank system with balls in it for surface area. Okay, oxygen is oxygen, O2. Okay, now to make ozone, you can make ozone 2 ways, using ultraviolet, or you can use it what's called corona discharge. And corona discharge is as simple as that. You got this wire and you got this wire. and you put electricity to it, and the little spark goes across the thing. Or you put a glass tube in it, and you put some metal in the middle of it, and you put some metal and this other here. And when that spark goes like that, and oxygen goes on the outside of that tube, encased in this steel or aluminum box or cage, when that oxygen goes through that, that spark splits the O2s into O1s. And the O1s are looking around going, man, I'm unstable. I got to grab onto stuff. And they grab onto an O2 and they come out and I'm an O3. Wow. We have Superman now, okay? This totally changes the world, okay? That oxygen thing, which we use every day, which is the most important thing, we have to have it every single second, becomes Mother Nature's disinfection. Ozone is natural. Ozone only lasts for 20 or 30 minutes, so it's very unstable. But it is so powerful that if you breathe it, you'll eat up your whole esophagus, everything can kill you, okay? So that's why people don't work with ozone a lot, because they don't understand it and it's got a reputation of being dangerous. But the benefits of being able to understand using it correctly are astronomical. Understanding that the thing could be composted in the first place, and not only the toilet, 2/3 of the organic waste that's created in the household comes from the kitchen. So all of the organics, including turkey bones, T-bones, cat litter, whatever else like that, you can put that in the composter. I install a separate garbage disposal sink with a 1-horse garbage disposal with a hand sprayer, and the way you clean off your dishes there first, then you wash them, and then you put them in the dishwasher for sterilization, okay? So what I believe is that by inventing what I would call inventions that are localized, that take care of the issues at the point of source. The inventions I have for the organics and the water are pretty good, but we need a trash compactor that you can take all of your plastics and all of your glass and you put it in the thing and you shut the door and it grinds it up and it washes it and it separates it and it puts it in a little bag, and the cooperative comes over and picks it up and gives you a credit. When you go to the grocery store, or anybody, this is the part that I don't think people, and it's not anybody's fault, we're not taking responsibility for our actions because we do not have the technology available to support the industries that we've created, which are using these plastics in a disposable fashion. So in changing society, we need the technology to be able to make it effective, to make that possible. And because of the capitalistic centralized system of the education system of setting the engineers that pipes have to be for sewage, this is where it's got to go back and say, you learned a great thing. It's wonderful for history. But if you're going to support whoever going to Mars or wherever, you better think about some water on the way. We do not realize, number one, that shit needs to not be treated like shit. And it needs to be respected, but we need the technology to do it. I believe I've been very fortunate in life to have had the opportunity to have been introduced to a host of individuals and persons who have supplied information to me that has given me a more holistic idea of technology, alternative technology, but now the possibility of providing that worldwide immediately through the cooperative existing network. 10% of humanity on the planet belongs to a cooperative. I can't think of a bigger market that's available with the product. So these pipes are crumbling, and there ain't enough money, and there isn't enough time, and people of my age are disappearing that have the knowledge about how to work with your hands. Everybody else has got this knowledge how to work with a computer. So I believe that decentralization has a real possibility now of not only getting some water and housing and everything to people, but it has the possibility of changing us from this capitalistic consumption philosophy of economics to a philosophy of economics of cooperation and recycling. With all of the materials that are already available, that are existing, that are here. They're laying in landfills. They're already, it's there. So Mr. Fuller said, Thomas Malthus, and Malthus saying that there'll never be enough because there's more people. And Fuller's point, which he made a good point about copper. Long time ago when they had the first telephone, it took copper line all the way to Japan with a boat laying the stuff all the way there. Right now you got a little piece of copper that's someplace somewhere that's talking to the whole world. Okay, so it's just doing more with less. This is what I've learned from Fuller, but I believe that I was blessed with the opportunity to use my hands and to meet people that gave me direction, that helped me in life. I just want to share this, and I think, which I tried a capitalistic idea, and that didn't work out because I was squashed by the government. The cooperative is a separate entity from the government, and the money that is worked with the cooperative stays with the cooperative. I believe the power can be redistributed back to the individual locations, communities, with their own money, with their own technologies. And I believe I've got the technologies to make that a possibility.
Well, it's pretty compelling stuff when you look at if you're going to do any kind of habitat in a resource scarce environment, then immediately you have to look at what's my air like, what's my water like, food, and then shelter. And it seems like your solutions really do take all of those considerations as starting points. So getting into specifics of the septic tank versus the bioresequencing.
Biomatter, so you got to have matter, biomatter, it's something that's organic. Resequencing, we're going to change it.
Yes.
Resequencing converter. I didn't do it. This is Gene Roddenberry. Like inventors, if you want to call inventors, we're just copycats. Okay. If you go to a septic tank, here's the way a septic tank works. It works on the anaerobic principles, because when you mix something with water and there's no oxygen, there's two kinds of organisms, aerobic, anaerobic. The anaerobic don't use oxygen. They create hydrogen sulfide and methane gas, and that's why they stink. They're very, very, very docile. They don't do much work. Okay, so in a septic tank, what ends up happening is the grease and the lighter stuff floats, the heavier stuff settles. They usually have several chambers of them. The latest idea is then you add oxygen to it to try and eat up some more of the stuff. But then the final disposition before the whole aerobic thing was the leach field or the drain field, which is aerobic. And so the whole thing is that you took this human excrement, which if you would have just dumped it on the ground, would have been aerobic. But no, we had to put it in a whole bunch of water to move it away because we're scared to death of it. So the whole thing about moving it away, you want to move it away. I mean, that's not the point, but it's how you're doing it and why you're doing it. And it's because we've always, like the first actually toilet invention used dirt, okay? It didn't use water. So Thomas Crapper and all these other guys that invented the toilet, they use water. The dirt thing, you can't move it very far, but it mixes with the dirt and it's got the organisms, and the human excrement has already got the organisms to create it. When life leaves us, the organisms take over. They're already in us, okay? They're just waiting for us to die. Everything's just waiting, ready. We're here. And then if you add the worms to it, which Aristotle called the intestines of the universe, whatever you think that they won't eat, they will eat. So the people who are worried about plastics and they come up with, oh, we've got a new worm to eat the plastic. These worms will eat anything. Now there's different worms, there's more aerobic, there's all kinds of stuff. That's why Mother Nature put all this stuff together. We separated it and screwed it up. And so then the septic idea, which then, if you go into the sewer idea, they moved it a whole bunch of distance or whatever, and they go through the first thing is to screen out all of the plastics and all of the underwear and everything else that came through the whole sewer system, sometimes a dead body. I mean, all kinds of stuff. Then it goes into this digestion thing or whatever else, and then they add oxygen to it, and then eventually they put some chlorine into it, and sometimes they even do ozone. In China, they use a lot of ozone in sewage treatment plants. That's always at the end. It should be at the beginning. Okay, so the ozone eats up organics. See, the septic, first of all, is anaerobic, so there's not much going on. And when you make it aerobic, it's only oxygen. But when you use ozone, the ozone, it's like the guy who wins the hot dog eating contest at Coney Island or something like that. I mean, you got the guy that eats 5 of them, and you got this guy that eats 50. This guy's the ozone guy. I mean, that's the difference between oxygen and ozone. It's just a totally different animal. But it's got to be controlled. Oxygen, you don't have to worry about it, okay? So in my whole system, this is financed, manufactured, installed, monitored, and maintained by the cooperative. Humans, this is where which I agree with the government, and I learned this part in trying to sell composters and gray waters and all these domes or whatever it was to the individuals, and those people saying, well, I'll take care of it, I'll do everything. They never do. People don't do it, they're human beings. And that's why the government gets upset, because they say, well, you're going to hurt the other guy, which I agree. So that's why, especially with water and sanitation, it needs to be a utility. But it can be a decentralized utility, having decentralized components that are working with a much more advanced technology, which is ozone, and is decentralized using composting instead of septics or sewers and pipes. So if you can make, for example, the toilets I use less than 2 cups of water to flush. They actually have it so you can lift the bowl and you can raise more water if you're going to defecate in it, worry about staining the thing. So Sealand makes an excellent toilet. With the amount of water and going to the composter, you reduce the amount of water, number one. The average consumption of water using a septic system at the moment is 28%. In commercial activities, it's like 80%. So you go to a downtown. All of the cities, the reason that they're great big tall buildings is that the pipes are cheap, and so the toilets can be stacked. Everything in all design for school and everything, they're going to say, what's the first class 101? 101 is the pipe. We're paying for the pipe. You don't care about what we're going to build, you're going to have water. So somebody says, well, I don't need the water. If that pipe is going by, the government's going to charge you for that existing pipe, even if you don't use it. And so this whole pipe thing, and we set up, and I mentioned to you about Calgary and the problems that you have in Canada, and it wasn't only Calgary, what the pipe did to businesses when it exploded, and $1 million people out of business and stuff. I mean, the ramifications of that technology are beyond belief. If we have a problem individually, it's individual, okay? So the strength to me, again, is having the technology to, first of all, build housing that doesn't blow away. So round usually works better. So the aspect of also this stick-built housing thing is very unnecessary when we have the capability of logically manufacturing the components. But we need to be able to manufacture components that make sense instead of this rectilinear. And so that's where the dome comes in, because it makes sense, but nobody ever put the roofing and anything together. So I think I've come up with some better ideas. Putting in Alaska and working with the Eskimo communities and working with these things above the Arctic Circle and making water disappear at 60 degrees below zero by using the heat from the composter to put it into the leach field and watching water evaporate, that was pretty impressive.
Just tell us a bit more about that, because that is super impressive. And for people who don't know, you are a grant and an award winner for your Alaskan toilet. And I'd like to just learn more about it.
Okay, well, the composting thing started when I was 35 or something, and I was trying to sell geodesic domes and composting clevises in Colorado. My brother-in-law and sister in Alaska sent me a one-way ticket to Fairbanks, and they were going to give me a job. He was working at the Usability Coal Company. He was going to give me a union job as a carpenter. So I went up there with a box of tools and nothing else. So I got there, and luckily, which as most of my life, somebody had just bought a geodesic dome kit and had no idea how to put it together. So it's from the big outdoors people, and I went there and I said, yeah, I know how to do this. And So I got a job. I built this great big geodesic, 45-foot geodesic dome in Healy, Alaska. And from then, I went down and got my girlfriend back in Colorado, and we loaded up my truck and drove up the Alcan Highway, pulling her Subaru. It was great, the dirt road, mud, whole trip. Got up there, and the whole dome thing had fallen apart. And so now we were living in this trailer at $500 a month, whoever. All of a sudden the phone rings and they said, Clint, can you re-roof the power plant? I had no idea how to do it. Sure. And so I got a job re-roofing the power plant, got some money out of that. And then Clevis called and said, hey, we sold a couple of Clevis mulchums. You want to put them in? And I said, sure. Who are they for? He said, it's for the government, U.S. National Guard. Okay, let me know. So I built 2 of these units. One had to go in Anchorage as a test model, and I sent you the pictures of wherever that 2-story thing. Okay, so I built all that. We had to manufacture it in my backyard, put it on my truck, drove it to Anchorage, set the first one up, put the next one on flights, and I went to this community called Selwick, which is a village that is near Kotzebue. It's in between Nome and Kotzebue. So my wife, Kathy, and I flew up there, and they flew us to the village with a couple Eskimos, and we stayed in the National Guard Armory in December and put this thing together, this 2-story outhouse. Eskimo says, how come you built 2-story outhouse in 1-story town? Well, this worked out pretty well. And the government said, well, we want more. So they put out a contract, but then the company called a lumber company took the bid away from me by copying my plans. And Clevis didn't support me, and so I said, well, Abby, this is not a good idea, bye-bye. So the government said, well, just between you and I, you seem to know what you're doing, and maybe if you came up with your own idea, we could come up with maybe some help. And so I said, okay. And so I came up with my own idea, and I got a contract for $10,000 to come up with my first composter. So I just copied the Clevis idea, just squished it down a little bit, sloping floor, and sold one to the National Guard, and they put it in, or we put it in, I put it in. And so it worked. And so he said, well, we want some more. And so we got a contract, and then I made several out of aluminum with another gentleman, and we welded them together, sprayed them with foam. And my ex-wife and I would go to these villages in the summertime, and we would install them. And so it was, I can't even tell you how wonderful it was. Just working with the native people and it's totally uncomprehendable. So we did this, and the native people loved us, and everybody was going great. And I actually ended up, we went from aluminum, then we went into fiberglass. And then I learned about what's called polyurea and polyenes. And so we started spraying polyurea.
That sounded like a really amazing experience working with the native people up there. Do you want to just expand on that a little bit?
I'll get emotional. Working with the native people showed me exactly how the white people have screwed the native people for years. So the money that comes to Alaska, when I got there, it was $6 billion had been spent putting in piped water and sewer. And 99% of it failed because of the culture. And the culture of the white person thinking that these native people were just here to put this in and go away, which they did. And then the native people were harbinged, were levied this responsibility of having to make money to be able to support the heating of the pipe. These people didn't have to do this before. They hunted and they gathered, okay? And they took care of their own excrement, and things were working well. And they were doing okay. And it's been done for millenniums, okay? Even if they had to move, they would move, okay? But when the pipe came in and these white people, well, I'm using white people, these different people, their attitude was they're putting this pipe in and now it's the Eskimos' problem. And so as with the problem with existing worldwide is the whole maintenance issue. So when the whole design goes in, nobody thinks about the future. and how it could change. So all of this money is $6 billion. I mean, for one example, on the North Slope, it's called, there was only 6 villages. And so the North Slope even came up with money. For a little 600 square foot house, which was from HUD, they were spending $437,000 per house of your money to put in a pipe that froze. Okay, and this is still going on. If they didn't put in the pipe, and so I'll go into the real story. So I did all this with the National Guard. NANA, North American Native Association, liked me. I became very good friends with a lot of Eskimos. And they actually supported it and wanted more. So in this village of Buckland, I went there first with a contract under, which was Governor Walter Hickel on the second administration, gave me 15, came to me, he said, what's your problem? And I said, well, they don't think an Eskimo's smart enough to be able to run this thing. And he said, what do you need? I said, I need an Eskimo. He said, well, what else do you need to do this? I said, $15,000. I had no idea. Well, I had an idea because I'd been to the villages before. And so next week I had $15,000 and Keiko called me up. He said, I got an Eskimo, go meet him. So I went to Buckland, met Lester Hadley, and this is my house. And he said, you're welcome to put this thing in. I can't help you. His wife told me, if it's worked, you're welcome in the village. If it doesn't work, you're not welcome here anymore. So I built this building, which I sent you the pictures of. It says Alaskan toilets in it. So I manufactured all that in Fairbanks, built the composter with the gray water, the whole thing. Flew it from Fairbanks to Anchorage, Anchorage to Kotzebue. In Kotzebue, I met it and had to rent a DC-3, stick it in the DC-3, me and the pilot and the co-pilot flew into Buckland, but on the landing, I'm a pilot also, so on the landing, a bunch of crosswinds, and there's nobody there where else at, so we had to do a go-around. So as we're coming back on the go-around and we're landing, and it's a kind of rough landing, all of a sudden the whole village is out there. And so we get out the plane, and I meet Lester and everything. I said, how come everybody's here? He said, well, the last time this happened, they crashed. So we wanted to watch. I said, okay. I said, okay, well, let's unload the plane. The plane. So anyway, I spent 2 weeks by myself working with another Eskimo, put that building together, put the toilet into the house. And it had its own water tank, which water came from the river. The city had their own filter system or whatever, which you'd have to go and get your water. So the way it works in the village, you go get the water and then you put it in your tank. So I had a 500-gallon tank, I had the composter, gray water tank, and I connected the Sealand toilet to this with what's called a utilidor. So it would get heat from the house, okay, and was insulated or whatever, so it would be okay. It was all panelized. With the water, I had to get rid of the water, the gray water. And so I came up with the idea, instead of venting the hot compost air from the compost just to the vent, I vented it into the water, into the pipe running to what's called an infiltrator, which is a plastic domed kind of leach field. And so the air would go into that and it just, the water, and it would just evaporate it. So on solid permafrost, at 60 degrees below zero, I could evaporate water. Okay, so this system worked, and the natives wanted more. So I got to do 2 more units. This was back in like 1996. After I'd left Alaska, they'd run me out of Alaska, the Corps of Engineers and everybody, we don't want you here. So in Minnesota, I reset up again, got a contract with the village, and came back with 2 more units, which these we attached to the house, which I sent you pictures of. So it's a little bit better operation. And we proved that we had 3 units working in that village. Senator Ted Stevens then came up with an idea of saying, okay, I've heard about this Alaskan thing. So I'm putting out an RFQ for a test for piped water and sewer, what's called the flush hull, which was just a holding tank, and they would come and dump it, and the Alaskan system. Okay, so I was in this bidding for this $3 million, $5 million contract or whatever. So I already had 3 units in there. I had a survey that was signed by the whole village that they wanted Alaskans. I had a native person go and ask, what would you like? They all signed it in their own handwriting, or sometimes an X or whatever. Willie Thomas, the mayor, called me one day. He said, Clint, the Corps of Engineers is up here and they've got their proposal. We think you should come up here. I flew from Fairbanks, went up to Kotzebue, got into Buckland. The Corps of Engineers had no idea I was there. I showed up for the meeting. The Corps of Engineers had a whole bunch of pie charts on the wall. They had done all of their own surveys. They had changed everything and so that nobody wanted the Alaskan system and everybody wanted pipe water and sewer. So through the diligence and the wonderfulness of the Corps of Engineers, I was screwed out of a $5 million contract of just that, of which then the Corps of Engineers came in and suggested that and proved that they had to move the village in order to do things from the other side of the river, okay, which was millions of dollars. 2 years ago now, with the flood, they just washed the whole village away. So what they put in went away. The interesting thing also in regards to getting down to the nutty grits about this, when I came back to Minnesota, this is where I tried to work. Okay, so the Alaskan thing, I did the Alaskan thing and proved it. I had the name Mr. Anuk, which means Mr. Shit in Yupik. And so leaving Alaska with nothing, I gave everything to my second wife and started another life in Minnesota. So I tried to bring my ideas there about reduced size leach field for the thing. Well, the government didn't like that either. And so instead of trying to work together, they actually changed the rules, which changed the law in Minnesota. So instead of what's called individual sewage treatment system, they changed it to individual subsurface sewage treatment system, which meant that everything had to be discharged subsurface, which was the rule, which when you go to the law says that any developer, any builder has to follow either being on a sewer or follow the rule of 7080, which has now changed from individual sewage treatment system, which included composting and everything else, to solely subsurface sewage treatment. So the work, when I tried to do this in Minnesota, I said, well, what if I don't discharge? They said, well, that's impossible. Oh, yeah? So then that lit a fire under me, and I said, okay, how do I find out about this stuff? So I knew about water a little bit, or whatever. But through other friends, I met people who worked for osmotics and the osmosis inventors in Minnesota. So these guys were the guys who worked with it. They weren't just like the guys who were taking orders. And so I worked with a couple guys, and I got a couple of contracts to build systems in northern Minnesota where septic systems were $30,000 because of the rock, and wells were another $40,000 because of the rock. And so my technologies were available, and so I sold about 5 or 6 systems with the water recycling system, with the work that these guys had educated me on. And so they built sort of it. And we were using high pressure pumps and what are called 4x40 membranes. We were using ultraviolet light, and it was working. And actually I sold one to the Robert Redford Natural Resources Defense Council office building in Santa Monica, California, which was the first and only recycled water system in all of California. I met Robert Redford, came down and said, who are you? The crazy guy. So we had that unit and it worked wherever, but it wasn't working as well as we wanted. And so I asked Joe I was working with, I said, what about this ozone thing? So we started and we changed to ozone. But we were still, it was very expensive in what we were doing. And so it worked, but the people weren't taking care of it, and that's the whole thing. So all of this technology, that's where you realize the more advanced it is, you just, I mean, right now you can't work on your car, okay? Back in the old days, for example, I could, in the truck I had to go to Alaska, I could climb in the engine and adjust it myself, okay? That's how easy it was. Well, that doesn't exist, okay? Well, the same thing with trying to do this water thing. When you're working with ozone, it needs to be, have somebody working with it knows what they're doing. And it needs to have the equipment that doesn't leak, and so it needs to be stainless steel, rubber gaskets get eaten up, there's a lot of different things. Plastics get brittle. So this is why it needs to be utility. So what I'm coming to is that the work that I've tried to do with the dome, which again, just trying to get a permit for a dome in the United States is impossible, okay? And what the problem in the United States through this capitalistic government regulation system has made it so that it's impossible to meet all of the regulations capitalistically, time-wise, everything else, okay? So they've made it so difficult that it's increased the amount of money based upon the existing technologies that they're utilizing. So this is why I've always kind of gone around the corner, okay, and say, why fight it, okay? I remember when I was in OCS in the military and they had what was called escape innovation. They took us candidates and they put us in a deuce and a half and they said, okay, you're gonna have to go from here to way over there tomorrow and get there, and you got a compass and there's gonna be a bunch of guys that are gonna try and capture you. Well, this didn't sound good to begin with. And when they capture you, what happens? Well, we're gonna take you to the Vietnamese camp and it's not gonna be nice, okay? It didn't sound good to me right away. So we're in this deuce and a half and they say, okay, jump out. Okay, so everybody jumps out and I'm standing there with another guy. I said, wait a minute. So we jump out, all of these guys come out of the rocks from everywhere and they're ready to tackle everybody. So we let the first rush go by and we just kind of run around the corner. There was only 4 of us that got out of that. Okay, so we didn't we didn't get caught. So this is part of what I learned about why go head on about this stuff, however, why not try and find a different avenue. And so the different avenue, by really following what is not totally available, and luckily, again, I've just been afforded the opportunity to work with this. Coming back to the Eskimo thing and about the native person, and especially even in the United States, or I don't care where you are, there are indigenous people here in Costa Rica too. They're worldwide. I mean, they're the first ones. This technology is available for them right now. And these are the people I want to help right now as far as doing it. I want to set up, they already have cooperatives. So when I was in Kotzebue, they have a cooperative that had the great big windmills. Okay. Senator Murkowski helped get the money for that. Brad Reeve, who was the general manager, a very good friend of mine. At that time, I didn't have the technologies to make it available, especially with the water, and especially when you're dealing with ice and freezing temperatures. Down here, it's totally different. With ozone, you've got humidity, so that's why you have to have an air dryer. So these are the things I've learned that I think are very valuable for different climates. So I don't care if you're in Siberia, or I don't care if you're in Hawaii, or the Philippines, or wherever. I believe that these technologies, with adjustments, can be made available, especially through the cooperative network via the internet, which I can tell you right now with all of my economics, I can build the total dome for less with the housing, with the water and the sanitation, total for less than $40,000.
That's wild.
Well, right now you can't buy a car for the average car in the United States is $47,000 and the average house is $425,000. Okay. I can build the entire house anywhere in the world right now for less than $40,000 with water, with sanitation. Now, I can't do it, but the cooperative can. All they need is basically the ozone generator and the air dryer, which can be manufactured locally also. The tanks are already there. The plumbing is already there. The half horsepower pumps are there. If they want to really get good about this stuff, we can make it smaller with smaller pumps. When you work with a cooperative, you get paid in credits or whatever it is. If you come up with an idea, instead of having this global business relationship of moving all this shit around the world or whatever, you share that idea and you receive the royalty for that. So if I come up with an idea and it's done, or if somebody in China comes up with an idea, the Human Endeavors Corporation pays that royalty back to that Chinese person for what that royalty does for worldwide. I understand how the whole global thing, globalization of business operates, but it doesn't look very good to me. I believe that by decentralization, first of all, the one thing in Costa Rica is called tranquility. You ask somebody, they say, man, I'm all nervous. I just want to get this job done. That's typical gringo. Oh, yeah. First thing, Costa Rica was tranquil, man, tranquil. In the Caribbean, they say, soon come, man, soon come. They're tranquil. But anyway, the basic thing I believe in life is if we can reduce the stress on humanity from what are called, what I believe are what are the human needs instead of the human wants. And we've designed a society based upon capitalism on human wants instead of needs. And so we need housing, we need water, we need sanitation, we need a little energy. When you reduce the amount of water you need and you reduce the size of the house and you reduce, you don't need as much energy. So all of these equations all have to be recalculated because what are they using as what's called the premises are based upon the history of existing technologies. And if we use different technologies, which I'm just trying to show the little bit that I've done here, okay, that this is possible. I believe this water thing that I've worked on, the sanitation thing is the number one, okay? But the water thing, the housing thing's a good idea too. But the water thing, I met the owners of Culligan, Connecticut. Bill Pryor was a very good friend of mine. These guys are the two top water softeners in the world. They came to me and talked to me about stuff and just rolled their eyes when I told them about recycling water because they realized their business was no more necessary. Water softener business now normally is a bunch of tanks and they filter it with a bunch of media and stuff like that. They don't even use ozone, okay? Back to ozone. Imagine all of the hotels in the world switching from chlorine and chemicals in their laundries to ozone in the swimming pool and the laundries to be able to recycle the water. Here in Costa Rica, the Hotel Barcelona uses 2 tanker loads of water a day at over $1,000 a tank, and mostly for the laundry, which is discharged without much treatment into a supposed septic system, which is running into the ocean. All of these things are possible. It's just a matter of being willing to accept change. And I realize change is not easy, but it's not that hard, okay? And it's not that, it doesn't hurt that much. But the opportunity and of total employment of not only Costa Rica, but all of these other, especially locally. And this is where, back to the farm person, well, I gotta go to the city, make me a job, you know, and that's it. You don't need the city no more, well, brother. You can make more money or credits, or whatever it is, stay in your local community, marry your high school sweetheart, wherever, have a family if you want, do whatever you want to. But we don't need this competition worldwide to try and screw each other. We need to be able to work together on this planet. And it's the technologies that can make that a reality.
Well, I mean, certainly that is an exciting viewpoint into a future world. Now, walk me through a few of the potentials here. So we've got more into the cooperatives. They're a source of credits. They produce electricity. They are taking in, it sounds like, kind of composted waste. So essentially, they're performing the duties of a municipality, if I'm hearing that correctly. What size do you see these cooperatives being? How many households would a cooperative touch base with? What kind of assets would they need? Trucks? Give me a broader vision here.
Okay, let's start with what exists. We can go to every house right now, walk into the house, jerk up the toilet, cap it off, put the vacuum toilets, and either next to the house or someplace like the house, there's this box. It could be in a big multiple-story building or it could be in the building. But it's this box that plugs in to the building. And it's got water in, it's got water out. It's got the composter with water in, water out. So right now, in order to make that happen, the cooperative would be able to would need to be able to manufacture this building, which comes in components. The whole size of this is less than the size of a car. And I can even make it smaller if it needs to be made smaller for smaller units. Right now I'm using the 55-gallon drums because they're cheap. Okay, I can use 30-gallon drums, I could use smaller ones. Not only me, but this is where I can teach the engineers and they can come up with a whole bunch of better ideas for even making it smaller and tinier, okay? So the whole thing, the composter, because I'm using that, that's pretty good size and it's cheap as far as the thing. The pumps, right now I'm using pumps that are this big. You can use the 12-volt pumps that are about this big. So the size of it is not that big a deal. Brain box that runs it is connected to the internet. And so when the cooperative uses its own money of its own bank, okay, to make a license with Clint. The Clint supplies all the information, then they manufacture it, they install it, they plug it into the internet, and they monitor it. And when you use some water, it calculates it, sends you a bill. Only for the water you use. You don't use any water, there's no charge. I can build this water recycling thing for less than $5,000. I can build my composter for less than $5,000. Before it was costing me $25,000 for each. You can't buy, right now they're trying to sell you a septic system that comes from Germany and Costa Rica for $7,200. Just to think, which is an aerobic thing. So what I'm saying is that the invention using these recycled tanks is the secret. Okay, so the cooperative can do this for retrofitting. I don't care if it's New York City. We can do this tomorrow, okay? And they already have, for big buildings, there's companies that are already recycling in the big buildings. But they're having to take the combined waste and they're going through a bunch of rigmarole. It'd be easier to separate it and put smaller composting on the 12th floor underneath the toilet that's on the 13th floor. Okay, so we could retrofit every big building if it had to be done too. So the cooperative supplies the money, they supply the manufacturing, they install it, they monitor it, they maintain it. The amount of composting that you get, and this is the hard part for people to believe, is insignificant, okay? When you take human excrement and 90% of it is water, okay? And you take urine when 99% of it is water. The real thing is that water that's used for flushing the toilet, okay? So you don't have that much hydrocarbons that are in the toilet. So you aren't removing that much soil. It's not a fertilizer factory. And so you don't need a big truck to come and get it. You go and drive a little Datsun pickup truck for a 20-story building, okay? So that isn't the big thing. The thing is that automatically it's going to be converting this to carbon dioxide and water vapor, recycling the water.
Question on the ozone. So if you're using this this arc, then I'm assuming it's got to have a relatively large electrical draw in order to produce sufficient ozone for whatever decontamination you're doing. So talk to me about the cost and running ozone and what breaks or what doesn't and that kind of thing.
Okay, the big thing about ozone is that it needs to have dry air. In most instances, they have what are called ceramic plates, which I haven't used those. Normally, it's this quartz tube that has like a wire brush or metal on the inside. It's got a little connection here and a connection here. So and it's in a aluminum cage. I could get it and show it to you. The quartz tube is a little bit smaller than the diameter of the tube. And so when air goes on the outside of this quartz tube, it's oxygen. But that little space that this air is going through, that this quartz tube is here, and this metal is here, and this other metal is here, this spark is going through that little air that's in between that quartz tube. Now, if it has moisture on it, that quartz tube will gum up with what's called nitric acid from the water. So that's why it has to have dry air. And that's a big thing about the tropics. That's why nobody does it here, because they didn't know. I've worked with different ozone systems, so I know the ones that work better. As that air is going past this quartz tube and this spark is here, there are different quantities of ozone that could be made based upon what's called the transformer. All this thing is just one transformer. That's all it is. The unit I'm using makes what's called 5 grams of ozone per hour, which is a pretty good amount. They have some that make like, they have little ozone units for hot tubs. They use like a millimeter, a very small amount. They have ozone for very small ones. They have ozone systems in China that are 500 grams per hour. I mean, these things could eat up a horse. That's how damn much they are. This 5 gram unit that I use and the heater use less than a hairdryer of electricity and run 24/7. And I'm pumping 1/2 horsepower water, 3/4 inch tubing through this water. My electric bill in my house here runs less than $20 a month. And I'm running this thing all the time. Now, the interesting thing about the ozone also, especially for a household and hotels or anything else, like one ozone system will take care of all of your water, gray water, rainwater, recycled water. You can also tee off of that and run it to your swimming pool. And that water can be ozonated with the pump of the swimming pool. It's called a venturi. So what happens is you have this box, it's making ozone like this. You have this little tube. And a venturi, where the pump goes through this pipe, and a venturi here, you turn the valve off, and then the water has to go through the venturi. So the venturi sucks the ozone that's being created, and it injects it into this water. And that water goes into the swimming pool, or goes into your washing machine.
In volumes, what kind of volumes, like let's say you've got that, you said 5 grams per hour, I believe. How much water can that disinfect at what kind of loads?
Now we want to talk about the quality of water. Okay, so you can have sewage, which is pretty high. Okay, so this is where the engineering comes in. Okay, normally for a swimming pool, the 5 grams is more than sufficient. The 5-gram unit, I pay $1,000 for. The 2 units, the air dryer, retail, I pay $2,000 for. Probably to manufacture it, you could probably make it for less than $500. If you get into large Olympic-sized swimming pools, for example, usually I have a chart on it, okay, and so it goes 10 grams, you go into bigger ones. If you have a water park and you have like more people, like if you have 1,000 people, so all of these things are adjustable. And so this is where a swimming pool company or the ozone engineer, which I'm not, they understand this, okay? And so like for example, with ozone, let's say the wine industry. So they have these big wine vats. They have a pressure washer that goes in, that's got a venturi that injects ozone into the pressure washer. So you clean the vats, no chemicals. Right now they use chemicals and all that water goes away. Same thing with the beer industry. All of the trucking industries, okay, same pressure washer could be used with ozone. Okay? The beauty about ozone is that it's not energy intensive. It's minuscule. I mean, when I asked you, like I get these from a company called Oxidation Technologies. A gentleman by the name of Joel, the owner of the place, very intelligent when it comes to ozone. Okay, kind of anal when you really talk to him about it, but he's very intelligent. So you want to know about how it all works and everything. I'm the kind of guy that has worked with the thing. I've understood when it leaked. I understand where the problems were and how to fix those sort of things. But ozone is very economical. The machine itself I've had here for 5 years, and I can't break it. One of the hardest things about ozone is that in venturi, if you don't have check valves, the water can back up. In various ones, the quartz tube, if it backs up, the generation of ozone creates a lot of heat. And so the heat and the water would bust the ceramic tube. The unit that I've got here right now, I've backed up water into it, so whatever this company did, they did something much better. So I've tried to screw this thing up as much as I could. I haven't been able to break it yet. Okay. So this is the part to me, I mean, I've had different kinds of issues with pumps, check valves, a lot of different things about learning things. But the secret about ozone, which kind of my ideas worked, is what's called contact time. And so normally they have the ozone with the venturi, you're only getting so much ozone in the water as it goes through, okay? So it's a big pipe, a little ozone, how much ozone? And normally they have what you call the contact tank, which kind of looks like a water softener tank, maybe about 60 gallons or something like that. My idea with the 4 tanks is that water is pumped out of the bottom tank. First of all, water is fed to the system. It's filled up from the initial tank. But then the pump sucks the water from the bottom tank, puts ozone into it, puts it in the top tank with ozone. Then the water has to go from that top tank into the next tank, then it's got to go down to the other tank, then it's got to go down back to the other tank, and it goes circulates. So it's got over 500 gallons of water contact time continuously. Okay, so this is a very patentable idea, however, but it's no need to go through that. So, but this idea, like the ozone guys have told me, this is a very good idea, Clint. Okay, so this idea can be duplicated for a lot of different aspects. This is a very smart thing. If with any kind of filtration, okay, so the first thing about water, somebody should tell you that you should kill it first. Okay, they don't. They want to filter it first. So normally with all that, I don't care if it's a reverse osmosis under your sink or whatever the deal is, everybody's filtering it first. They should kill it first. Okay. Because if you don't kill it first, the bacteria builds up on the filters and builds up on the carbon, and it goes on. And by the time it gets to the membrane, then you got a problem.
That totally makes sense to me. I could absolutely see that. So essentially, you're saying a lot of people get it wrong because they're trying to use less ozone by filtering it first, but in the full cycle, if they use the ozone with a heavier load, there would still be residual ozone as it's going through the filter and everything else, so it would be much more effective. Longer contact time.
Okay, well, now this is what you just mentioned about the ozone is important. Okay, now this ozone is pretty caustic stuff, so guess what? You can't run it through the filter because it's going to eat up the filter. But guess what? It doesn't last for 20 or 30 minutes. So guess what? You have what's called an on-off switch. So you run a system to kill and treat all the water first. Okay, and so like with a heavy load of what's called BOD, biochemical oxygen demand, or TSS, total dissolved salts or solids, suspended solids, whatever you want to call it, toilet paper, I don't care what you want to call it. Okay, you put it in this first tank of mine, and you take that nasty water and you pump it through that fourth thing of ozone. That ozone is going to eat up that stuff. Okay. And what it doesn't eat up is going to settle to the bottom of those tanks. Okay. By the time it gets to the fourth tank, there ain't much left. Okay. Now I also have a return on the ozone that goes into the first primary tank, so I'm actually disinfecting and treating that also. So there's a myriad of different things going on. That bottom tank, through this whole system, I'm assuming still has some ozone in it. Okay. Now, if you really wanted to have, and you had to be running it, carbon takes out ozone. So you could take and you could run ozonated water and you could run it through carbon and the carbon would take it out. But that's not a safe bet. Okay. The safer bet is to allow the ozone to die. And so when I run the system, I kill everything for whatever time, whatever it is, and then it shuts down. Okay. Now the water that's in that system that has ozone, the ozone valve shuts off. The pump turns back on, circulates that water, but now there's no ozone in the water, but it's all dead, cleaned up water. Now the reverse osmosis pump kicks in. That water is supplying the pressure, and the water for the reverse osmosis 12 volt, $150 pump, which I used to have $800 pumps, 800 psi. And it puts it through a small 10-inch sediment filter and 2 little carbon filters just in case there's anything going on, which you can buy for less than $50. And then it goes through the reverse osmosis membranes, which I get from Amazon for less than $25. A system, when I first got into this working with the ozone guys, the system they manufactured for me cost me $20,000. And I was selling it, and for these people it was a lot of money, but it worked. But it was big. So when I came here, I went back to my other idea about what was available and what could be smaller. And so I just went to Amazon, and there was a unit that was actually put together that had it's called a bigger membrane and a higher pressure pump. It made 500 gallons of water a day. Okay, so I got a bunch of those, or I got several of those, and I hauled those around Costa Rica, and when I lived in Mexico, and I worked the hell out of that thing. And it worked great, okay, and it made a lot of water. So it did, in this size, what was costing me $20,000 before, which now I could get from Amazon for $500. I took that unit apart. The membrane that they had was, it's called the side flow membrane. It's not available everywhere, and it costs a little bit more money, but it makes more water. I went back to just the normal membranes that you can buy that are the cheap ones. And I put 3 of them. And I just used the same high pressure pump. This 12-volt pump makes 150 PSI. I can make the same water, the same quality, the same pressure, the same amount that the $20,000 one was doing for $500.
That's great. Another question. Have you looked at ionization? People using metals, gold, silver, copper to clean water.
They've done that, and a lot of people do that even for swimming pools, wherever they try and do that. I don't understand totally about ionization or whatever, and they have their reasons for it. But what I understand so far is that if you want clean water, number one is reverse osmosis. That's all there is to it. So whatever the aspects of alkaline water and all these other things that they talk about. So, for example, like in the swimming pool business, they have what are called saltwater pools now. Okay, so everybody thinks this is a great deal. Well, so that's what this little thing is, this ozone, this saltwater generator. The saltwater generator is made by putting salt in the pool, which electrically is converted to chlorine. So the saltwater pools are chlorine pools. Okay, so it's no different. Okay, it's actually worse because you're having to buy the salt. And so, again, chlorine does not kill everything, okay? And chlorine does not kill cryptosporidium. The swimming pools in the United States, I think it was like over 60% of them all tested high for cryptosporidium, all public swimming pools. All Olympic swimming pools are ozone. All of the high-class hotels, swimming pools are ozone. All of the high-class and smart laundries are ozone. So there's the whole thing about water and drinking water and how you do water and everything. I have no knowledge to even compete or argue with that other aspect. All I know is that ozone should be used number one. Okay, so whatever the alkaline thing does or whatever the whole thing is, I'm not really sure. But I do know that if I kill everything first, that's healthy. And then if I can filter everything out of it second and start with 0, then somebody say, well, you have to have minerals for your body and you can't just drink 0 water and that sort of thing. Well, that's a bunch of BS in the first place. Okay, you don't get your minerals from water, you get your minerals from your food. Okay, you don't drink enough water to get enough minerals to supply what you need daily, okay? If the reverse osmosis water does not come out pure 0. In my case, it does because I'm using rainwater, but normally there are some minerals in it. Like, for example, in order to even know that my machine is running correctly, somebody say, well, you have to have a whole bunch of documentation, you got to test all this stuff, you got to do everything. The only thing you got to know is that what goes into the membrane and what comes out of the membrane. The membrane has been tested by National Sanitation Foundation, and if it reaches what's called a 96% efficiency, that means like if the TDS is 100 and the water is, this is coming in and this is going out, and it's down to like 3, that's 96% efficient, okay? When that starts going to 10 and it goes to 15 and stuff like that, now you're at 95, 90%. That means that you are not meeting the required government approved, regulated measurement, okay? So the only thing you got to measure is the end product quality difference. That membrane is meeting its required testing parameters. Doesn't have anything to do with Clint's pumps or the filters or anything else like that. All you got to know is what's going in, what's going out. Now you can tell much more about it because with the filters, we have pressure and you have flow gauges and flow meters. So the only thing you need in the brain box is just some pressure gauges and some flow meters to tell how this thing is operating. So it's not that much. It's not big a deal. It's not that hard.
Question for you regarding the geodesic domes themselves. With your grooved paneling, one thing that seems like an obvious benefit is the ability to move water. So does your dome design capture the water that lands on it so that you can recapture it and use it in your system?
Okay, imagine this. Like this geodesic dome is made out of fiberglass or plastic. Imagine that you had some great big round ship and you just turned it upside down. Okay, so you got this plastic ball that's there. Okay, so it's going to rain on this ball and it comes down. The one smart thing I've done about this dome I want to go back to also. The reason I've got all skylights is that because in construction you want to have angles that make strength. Okay, but when you have surface area, you have to have support. Okay, so when triangles before, I used to have plywood and used to have members in order to support it. I took that out because I made domed windows, skylights now that are only this thick. So I've reduced the amount of material for the surface area by making skylights of the whole thing. Okay. Now when it rains on this thing, it's all lipped over, so the water comes floating down to this pie-shaped foundation, which just happens to have an extension on the outside of the dome, which you walk around the whole thing. So if it's floating on the water, you have this platform, okay? So water is coming down and it's all got a nice floor there, except it's grilled and it's filtered down and the water goes into the tanks. So there are no gutters, nothing. Just runs down on the surface of the dome, runs onto the platform that you're there, and it seeps into the tanks. Now, this water is not clean, okay? Well, and it's got most of the dirt and stuff out of it, but it's got the leaves and the big junk out of it, okay?
Bird poo, whatever.
Each one of those tanks, right, well, the bird poo will be dissolved and it's going to go down into the tanks also, okay? So this is going to be not good water, okay? But each one of those tanks is ozonated, okay? And so all of that water is killed all the time. The thing about water is you just can't let it be standing by itself. Okay, so you gotta kill it. And so this is the whole thing about having the water in the tanks is that you would, one of the biggest things is keeping it from sunlight. Okay, so all of the tanks would have to be lined on the inside with a coating so that the light doesn't penetrate it. Light is the living factor. Okay, so you cut the light out, then you keep keep the water dark. You don't have any problems as far as it, so you can store it. The tanks are accessible, so they can all be cleaned. All the lids come out. The whole floor on the thing is all pieces, so it all comes apart. Everything all comes apart, so it's all accessible. Everything's there. But the whole thing, if you can imagine this, I look at this as like being a yacht. Okay, I mean, this is no different than what the whole yachting industry is about. I mean, the toilets I use are those kind of toilets. Okay, I mean, the $1 million yachts use these same toilets. Okay, Sealand toilets. And so I look at this thing as being a self-contained thing, which is like a boat. Okay, or should be. Right at the moment, most boats don't have the technology to compost and take care of the stuff like I'm doing. They don't have the ozone. They don't have these things. So, I mean, not only the cooperative industry, but the housing thing, I mean, you can just go on and on and on. I mean, the marine industry, I mean, where do you end? Wherever a person is going to pee, you got a business, okay? So the real thing comes down, the dome is a nice thing, the water thing is a nice thing, but the composter, which I didn't invent the composter, I just improved it, okay? And the whole thing about composting is just like you said, well, somebody's got to dink around with it, and you got to shovel and you got to do that sort of thing. You got to be a farmer, you got to be a hippie, you don't have to be any of that stuff, okay? You need the technology to just mix it up. and to be able to move it around. That's all it is. And so in my life, I've learned that certain things corrode, especially human excrement stuff is very corrosive stuff. So you can't be using just any kind of material. So the plastics work fine. Okay? And so working with these things, again, it's just going to that next step with the engineer and saying, well, how can we improve this? And somebody instead of saying, well, I don't want to deal with shit. You know, and I say, well, you better get used to it because you do it every day. Okay, so get over it. Okay, I mean, this is, I mean, the whole trip about the human bodily functions. I mean, I never had any children. I doubt that I could even change a diaper. You know, I mean, I would, but I've actually humanly crawled inside these compost tanks in order to have to fix things. Okay. And there was no odor, there was no problem. There's some toilet paper laying around or something like that. But I've been in these things, and I didn't get sick. I didn't have a problem as far as it, because it's natural. Once it goes into that aerobic thing, it's not safe that you can just dink around with it, okay? But it's now in its natural environment. Once you put it in that water, you just mess the whole deal up. You just you compounded the problem.
What kind of volumes are we talking about when we're looking at how much water is needed for a household of, and you can do one person, 3 people, 5 people, whatever. I'm just thinking about the ratio, cistern to lodging, and how much of that is kind of accessible drinking water and how much of that is in process.
Okay, well, first of all, let's start with the standard. So the standard at the moment is between 75 and 100 gallons of water per person per day, depending upon where you live. Actually, in Arizona, which was kind of stupid, it's like 135 gallons of water a day. But most of it, they're calculating it by the water that's being used for the landscaping or the irrigation for the golf courses, okay? So that's in their calculations and what is being necessarily supplied, okay? So in reality, it comes down to if you're using the normal is a 3-gallon toilet, okay, so now it's 1.6, but even you flush it twice. So basically the human needs, with the existing system, about 50 gallons to 75 gallons of water per person per day, considering the laundry. Okay. So the toilet normally is 28%. It used to be 48% of the consumption of the water. When they got it from the 5-gallon to the 3-gallon to the 1.6, it reduced it to 28%. Okay, so at the moment, the toilet uses 28%. The laundry uses it's almost another 20%. And you've got the sinks and whatever down the line. So it all comes about, like I'm saying, between 50 and 75 gallons of water. If you go to all the different states, they'll say that much. Okay, so my toilets, or the Sealand toilets, reduce the amount of water from 28% down to like 5%. Okay. The laundry, you're still going to use this water for the laundry. Okay. And you're still going to use the water for brushing your teeth. And you're still going to use the water for the shower. And you're still going to use the water for the dishwasher. But all of that water, 100% of that water is recyclable. So we can recycle 95% of the amount of water. And we're only going to lose 5%. Now that 5% that we just supposedly lost, we just flushed into the composter or the biomatter resequencing converter, which now aerobically and through evaporation, or forget the word, that water is now going to turn into water vapor in this box. And normally we just shit canned it, okay? But in this case, my new idea is the dehumidifier. So we have a stainless steel or plastic dehumidifier, uses a little bit of energy. And that water vapor that is not toilet to tap, is toilet to evaporation to dehumidification, which returns it to the primary tank, and you get your 5% back. Now, if you went to the supermarket and you bought a bottle of milk, or you got some juice, or bought some beer, or you had some guys over for the Super Bowl and were drinking a bunch of beer, and they had to pee. Well, you just got some free water. Okay, now nobody shows up, and there's no water around. And I live where? Well, I live in the desert. I live in Arizona. The humidity level in Arizona, in Phoenix, is 20%. Here in Costa Rica, it's between 80 and 100. Okay. In the United States, it's usually 60%. If you need to, you can get the water from the air using the dehumidifier. But the first thing is the problem is the toilet. Because we use 28% of the water right off the bat. Okay, so when everybody, all the engineers and all the architects, well, the engineers only, that is a fixed in their equation at the moment. It's fixed. They don't change it. And so every time they calculate and every time they do a job, every time that number is fixed. I'm saying we can change that number. And when they fix that number, then they are responsible for getting rid of that number, okay, which costs some more money. Okay, so number one, you're paying for more water to use it once, and then you got to pay to get rid of it. Whereas, once you get free water, which you don't need the government, you don't need it from the river, don't need it from the... See, the government controls the river, they control the groundwater. They don't control the air. And this is where the cooperative can control the air with the technology, not the government. And so if you, and this is coming to Costa Rica, not only gave me the opportunity, but seeing from an international perspective, the differences, like when I lived in Minnesota and lived in Colorado and lived in Louisiana and different, especially in Alaska, I mean, it's cold, it's real frozen. But when people said in Arizona, we don't have any water, I never even thought about humidity. But somebody said, well, my God, it takes way too much energy for humidity to get enough water to flush the toilet. Well, you're right, okay? So all of these things, you've got to just back up and say, well, why are we flushing the toilet with 5 gallons of water? Well, they said, well, we'll use less, okay? Well, then they used less. Then they found out there wasn't enough water to get the stuff to the pipe. So a lot of the 1.6s always had to be flushed twice. So they're back to 3. And it was solely for transportation because the septic tank had to be located by regulation at least 10 feet from the foundation of the existing building. Can't be 1 foot, okay, it has to be 10 feet. And the leach field has to be a whole nother direction and another amount depending upon whatever, and deep or whatever else. Hell, I've seen leach fields that are hundreds of thousands of dollars, okay, just to get rid of the water, okay? And so this whole thing is that you got to have all of this water so we can pollute it once to do this anaerobic digestion, at best aerobic digestion. It's the best they do, okay? And then try and get some sort of a thing taken care of. And so their best idea at the moment, is, well, like in California, they're going to inject it in the ground, and then they claim that they can pull it out of the ground. And they're, the whole thing about this water reuse thing, they're trying to build these reverse osmosis plants to take this water and then bring it back to the people, okay, through more pipes, purple pipes now, only to use it for the toilet and irrigation. None of them. Well, in Singapore, for example, they do use what's called new water. But in Singapore, it's a community, okay, it's close and they got pipes and everything else. It's possible, okay. But you can't do this in rural communities, okay? And so the whole new water thing, they're using reverse osmosis, okay? But they're going through a lot of money and a lot of pumps and a lot of pipes, and it's just all unnecessary. It's all based upon existing premises that are outdated.
So if you were going to build, let's say, a floating one of these domes, talk to me about how you would float it. First of all, are you using those 35-gallon drums, or are you using a molded pie-shaped, uh, you know, hollow thing for flotation? You walk me through the process, because I mean that sounds cool.
Well, in this little thing that you see here, you can see it. Let's say that this is 2 feet thick. They're pie-shaped tanks. They're just like little boats. Okay, so you got 15 boats that are bolted together. Okay, so they're just flat. Okay, so all it is, we're going to make molds that are just pie-shaped, 2 foot, 1 foot, whatever thickness we want to do them. And then they've got lids on them, okay? So the dome attaches to that. We have to have some bolts and stuff like that to make it happen. But basically, the same thing as if you were pouring a concrete foundation. I mean, you have form boards and so you pour the concrete, okay? In this case, the form boards are the molds. And the water becomes the concrete. And so it's no more than just making these pie-shaped molds, okay? So one of the best ideas I would have would be you go to a place and you get a backhoe or something and you dig a little dirt and you make a pond. You line that pond and you fill it full of water, or you don't even fill it full of water, but you just take my pie-shaped things, you start bolting them together, you put the lids on top of them, you start the geodesic panels are all bolted together, okay? So everything bolts together. So the pie shape at first, it's all flat, it's all bolted together, and you just put the whole dome bolted all together. The whole interior, which is the beauty about domes again, because the interior is not supporting the roof, as the interiors in rectilinear construction, the interior walls can be made out of cardboard, okay? I mean, here in Costa Rica, they have woods that's called formoleta that's almost like balsa, okay? I mean, it's so light, it's like a feather. And it's dirt cheap. I mean, and you could build it out of that if you had to or whatever. So another aspect of the geodesic thing is it reduces the cost of your interior structure, of your framing and everything. So there's all kinds of advantage geodesically.
Now, with the geodesics, can you tie into the roof? Like, let's say for the second floor, instead of just relying on the compression members of the vertical upright wall, could you not tie into the wall or the exterior of the geodesic dome for the second floor, at least partially?
You can, and we used to do that, and that's how we used to support the second floor before. Okay, and so you could tie into the members of the dome. But in doing that, again, you have the dome expansion and contraction. But the real thing is that back in the old days, when we used to have to sheetrock it or whatever, it was a pain in the ass because you always had to cut these little triangles and all this other sort of crap. It's easier, like if you ever remember the geodesic dome that was built in Toronto, I think it was, that by Buckminster Fuller, there was this great big plastic dome or whatever.
Montreal.
It was the world. Okay. Montreal, I'm sorry. If you look at that, that was the idea, that the whole inside was all supporting itself. It was all, nothing connected to the dome. And that's the beauty about the dome. The dome should just be used to enclose whatever you want to build that doesn't need any exterior protection from the environment. Okay? So you can have open balconies, you can have closed or whatever else, but you don't need all of that support. And connecting to the dome is not unnecessary, especially when you have like cantilevers, okay? And so a lot of construction I've done uses cantilevers very architecturally, and it's very nice. Start doing things. So to me, I've built several domes where we ran the floors into the dome itself. It's a pain in the ass.
Okay, so back to the floating thing then for a minute. Um, is that gonna be expensive? Those 'cause you gotta probably get them molded, whatever. Like that's gonna be a pain in the ass and kind of expensive. But okay, assuming we figure that part out, you now have a nice floating base. You've got a floating dock now, and you've put a dome on the dock. Really?
So now you move in your water and sanitation equipment. Like, this whole thing can be all pieces.
Yeah.
This is one whole section of a piece. This is the piece that goes together. So these totally can be manufactured, okay, put together. So all of these components would be all made at the factory. They would all bolt together.
Now,
Big
another
thing.
question that I had is on the recycling. Recycling is kind of one of these things that is such a good idea in principle, but the results seem so bad across the board. It seems like it's really hard to actually recycle. So I think I'm curious, you mentioned some things that were interesting. What is your vision for being able to actually have great recycling systems? What kind of cleaning or processing do you envision in terms of feeding back into these co-ops?
Okay, let's take an example of our own human existence. Okay, so you got a house. So the first thing you got to go is you got to get some food, and you got to get some toilet paper, and you got to get some other stuff. And you got some plastic bottles, and you got some stuff. Okay, so you're living, and so you use some shampoo and you use some soap and everything else. Yeah. Well, the soap goes down the drain, so the water, we're going to take care of that. But that plastic bottle, what are you going to do with that? Okay, well, normally you just throw it away and it ends up who knows where. Okay, before it was being sent to China, right? All of the shit was being moved all around the world because nobody wanted to deal with it. And especially when they had dirty stuff, okay? And I'm not talking dirty, but I mean contaminated. And that's why China stopped, because everybody started sending us some not clean stuff. Okay, saying we
Garbage.
Okay, well, normally in a household, you don't have too much radioactive stuff, so it's not too bad. And even in most businesses, it's not too bad. I mean, like the old photo business used to be pretty bad with the petrochemicals and stuff like that. Used to be pretty bad stuff. That would be hard to deal with, okay? If I had to deal with it, I'd throw that stuff in the composter and I'd let the worms think about it, okay? That's how much faith I have in the composter, okay?
You still have to give me an overview of what the composter encapsulates, because when I was looking at your drawings, I could see that there were, especially the newest version, you've got the IBC, you've got the drop-in kind of screen, you have a couple augers and some screws. It looked like an oxygenator that maybe spun. I couldn't tell if it spun or not, but I didn't see any vermiculture pieces in that that I could see.
Well, the vermiculture are worms that you just add to it. But see, can you see anything here?
Yeah, I can see that. So, do those spin? They look like they do.
See the one on the left is spinning right now.
Oh, it is spinning. Yeah.
Okay, so there's just one little motor on that. This is view here. This is a composter, swimming pool. Here's the primary, and so it's being ozonated right now and the water recirculating. Here's the tanks. Here's the ozone generator, air dryer, pumps, reverse osmosis unit, and some of the molds. Mold we're working on now. It's kind of the skylight looking thing.
Now, can you look inside that cabinet one more time?
Sure. Okay. Ozone generator, air dryer. This pump takes the water and circulates it. This pump uses it to feed the water. This pump is used to supply the pressure. While this pump is running, it's supplying water. It feeds this pump, which is a reverse osmosis, which feeds the water to the membranes, which the water, good water, goes to this pressure tank. The thing about reverse osmosis water is that you have good water and you have bad water. The water called bad water is returned via here. So we never lose anything in the reverse osmosis. Like other engineers claim you lose. I don't lose any water.
Now, if you're not losing the water, then hypothetically, the total dissolved solids would be slowly rising continually in that sort of, not bad, but the water tank that you need to reuse. Now, I suppose that if you're refilling with rainwater continually as well, that maybe doesn't become an issue. I'm not sure.
Correct, it becomes diluted. But if it reaches such a high state, for example, like we used to run it almost up to 2,000 total dissolved salts before we would discharge it to the composter. And the composter converts it to water vapor, which is distilled, and we return it back.
So where's the composter?
Well, the biomatter resequencing converter.
Oh, but that one was empty, right?
Correct. That's not in use. Okay, so that what I put together, please understand, what I just showed you here is duct tape and Band-Aids and shit that I've been carrying around for 5 years, putting it together with nothing, okay? These are prototypes, okay? This is not the finished product, okay?
Yeah.
Finished product would be a nice cabinet. The pumps all need to be on the floor, totally different. But the aspect of it that is the beauty about reverse osmosis is that all the engineers will tell you that you lose 50% to 75% of your water normally because the concentrate is never recycled. What I learned from the osmosis guys, when they build big stuff, like when I worked with them, they built bottled water plants. Okay, we worked on one weekend or whatever in this community that made bottled water. I mean, hundreds of thousands of gallons of bottled a day. Okay, so they have big membranes, big pumps, big. Okay, so I learned from them about all these things. But with a concentrate, they had to discharge the concentrate. Okay, they couldn't recycle it. Now, when they worked for other kind of chemical industries that needed to recycle the water, for example, the computer industry, where you have to have very clean water, okay? They could actually flocculate the water and have shit drop out of it and that sort of thing. But that water, they could reverse osmosis and they could recycle that water. A lot of times they could take the concentrate and they could recycle that back into their system, okay? When you have a pressurized in system, you can't put the concentrate back into it. You have to have a depressurized system. So what I've got here by having that first tank is a depressurized abatable system to be able to return the concentrate.
Makes sense. So what are your challenges now? I mean, let's say that there was a cooperative somewhere that said, hey, Clint, we've got, I don't know, a couple $100,000. We want to build a prototype. We want to get started. What would that look like? Walk me through it.
Well, you just hit it right there, okay? So somebody comes here and they say, okay, what's it going to take? I want them, well, let's say it's somebody in Canada, okay? Let's say a group in Canada, which would be perfect because you got rural villages. I mean, you got the same thing Alaska. I mean, you got much more of a need than the United States. And you've got cooperatives that already exist, okay? Okay, so let's say, it's a good Canadian name, Francois. Okay, here's the deal. We need to finish these molds that I've got now to make a fiberglass dome. Okay, I've got, this is wonderful also, I ran into, when I'm doing my own fiberglass work, at 77 years old, it's not much fun, okay? So when I went to buy some materials, I talked to the guy and I said, Ricardo, is there some, fiberglass people that need some work? And he said, yeah, I know a guy. So Oscar shows up one day and he says, well, Clint, I'm kind of an old guy, but he knows what he's doing. And I said, well, so how old are you? And he goes, well, I'm 70 years old. I said, well, I'm 77. You ready to go to work? So he knows the fiberglass. So I've got good people here to make the first dome that we can make out of fiberglass first. We need to make a prototype. That my stuff here, we need to make new stuff. I estimate that we need probably $50,000 to $100,000 to get this first prototype done.
And what does that build? What do you expect? Like, what do you think that money would go towards?
I think we could do a complete 34-foot geodesic dome on the foundation with the water and sanitation, a complete package. The energy thing, we're going to still plug into the co-op as far as it. We can make our own photovoltaics or wind chargers or whatever thing somebody. I like the idea of what's called. Well, there's different kinds of wheels. Okay, flywheel generation is not very interesting. So I would say between 50 and 100,000 to make this prototype. Okay, they can legally own the prototype. Okay, I mean we take care of this legally as far as whatever. Okay, we prove how much this cost to make everything, so we have a basis from that. With those molds, we can make more fiberglass domes. Okay, and we'll know what that cost is. But the real advantage would be then to move into rotational molding. The fiberglass is expensive and it's time consuming and it's environmental and a whole bunch of other things. To do the rotational molding, there's actually used equipment in the United States for rotational molding. Okay, out of Ohio, there's a big company that sells this Plastimex or something. Okay, so I've looked into it, and there's different kinds of rotational molding. We just need small. That's going to cost probably $50,000 to $100,000 to get that and the molds to move into rotational molding. So if we did one, or if we did another one, in a different one, it would probably still need that same $100,000 to get into rotational molding. To do fiberglass, probably $20,000 to build the molds. But it makes a nice product, beautiful, and could be done. But the real thing would be the rotational molding of the recycled plastics, because the plastics are virtually for free and available worldwide.
Difficulty, I think, would be getting a relatively clean source and getting a reasonable product. Like, I know the source material is free, but it's hard to work with.
Well, rotational molding is not. Okay, so if you look into the recycled plastics industry, I mean, if you follow it a bit, you go to India and see what they're doing with extrusion. Okay, there are guys that are making. I talked with a guy out of India, like the corrugated tin roofs or whatever. They make that out of recycled plastics now. It's called extrusion or compression. Okay, so you take, well, the only thing you have to do with plastic is separate it. Okay, get whatever is whatever. And all I got to do is wash it, or the first thing you do is you cut it up. Okay, so they have these machines that chop all this stuff up. Got big stuff. You don't need a big one. You need to have the stuff. You need to take the labels off or whatever. There's a little bit of hand operation on the stuff. But then you put it in the chopper. It goes through this washing thing or whatever, which we can recycle the water and clean the water. See, that's what they don't have. They need my stuff for this. Now you have these little chips, and they're all clean. That's all you need. They go in a bag. Okay, the bag sits there. So now rotational molding is no more than a steel mold with a lid on it where you pour X number of pounds or kilograms into it of this recycled, washed up Coke bottles, PET, and you make your part. Okay? So right now, like I'm paying $30 a gallon for fiberglass resin here. And to make one panel, it's costing me about $100 between the labor and the material. So at 75 panels or whatever, it would cost me about $8,000 to make that dome. Out of recycled plastics, I believe we could make it for probably $2,000. The only energy you need is the heat, okay? And so in rotational molding, you have to heat it up to 350 degrees Fahrenheit. Okay, so that's where they have, like, normally they have gas burners. They have ovens, okay? They build a structure and it rotates and it rolls around like this. But it only takes an hour. So you put it on what's called the arm, bolt it on there, moves into the oven, goes in there for 20 minutes, comes out, cools down for 20 minutes, takes 20 minutes to take it out of the part and put the part back together. Every hour you can make a part. You can do this 24 hours a day, okay? But using, to me, what are recycled plastics, I mean, you've probably seen this in India, the rivers are so thick you can walk across the river on the plastic. They have no alternative of what to do with the shit in plastic. If anybody's using plastic recycled, they're trying to make existing technologies. They're making bricks, they're making tiles, they're making roofing tiles for square buildings, okay? They're competing against existing virgin products that are less expensive. And that's why the recycling industry of plastics is going nowhere, because they're competing against a market that's getting free oil. And so the thing is that you have to make a different product. And so I'm making products that are totally different, that there's no competition in it, and especially geodesically.
Now, speaking of your domes, when you make a dome, the panels aren't uniform based on the style of the dome. Isn't that correct? You have to have at least several different panels. What number of different panels variations are required to build your dome?
There's what's called frequency in domes, okay? 1 frequency, 2, 3, 4, 5, 6, 7. That means how many times you divide up the triangle. Every time you divide it up, you usually increase the frequency, which increases the amount of different triangles that are going to be required. In my construction, I've built 2 frequency and 3 frequency domes, which only require 2 different sizes of panels. Small panels make pentagons and large panels make hexagons. There's only 2 sizes. The only time you change from that is when you go to a 4 frequency dome, which will go to probably 5 or 6 different triangles. But there's no need to go to that size unless you want to exceed a diameter of over 60 feet. So in my case, I only, like, to make this sandwich construction fiberglass with the skylight, I need 6 molds. I need a base for the small, I need a top, and I need a skylight. I need a base for the large, a top, and a skylight. With rotational molding, we'll only need 4 because the top and the bottom are molded together. They don't have to be connected as they have to do with fiberglass. So the fiberglass I'm having to do it because it's cost effective that I can afford. I initially, if you saw it, I actually got a steel mold that I started with to do rotational molding that I used as my primary to start the fiberglass. But the rotational molding doesn't take a lot of intelligence to do, and it doesn't take a lot of skill. For example, doing the fiberglass, you have to know what you're doing. So to roll out fiberglass, to get it, to give the gel coat, to do the timing, to do the hardener, to do the waxing, it's a lot of, you gotta have a little experience. Rotational molding, all you gotta know is you dump the plastic in that thing, you put the lid on, you punch the button, you take the part out, you take the part in. That's all you gotta know. Okay? Keep it clean. Okay? Don't hurt yourself. Okay? But the source is, this is what I'm trying to get to, is that the important part is where is the material? Okay, I don't care where you are, where am I going to get what I need to work with? Whenever, like if you're a Tom Hanks in Castaway, you better find something to help you do something. Okay, so it's the same shit. Okay, so like when I was in Alaska, when you go to these villages, if you don't have what's with you, there ain't no hardware store. There's no cafe, there's no hotel, there's nothing. Okay. I mean, they're just houses and these people, okay? So when we went there, I mean, luckily we were able to stay in the armory, okay, the National Guard Army. Otherwise, I mean, you aren't even welcome in the village unless there's a reason to be there. That's why it was extremely wonderful for Kathy and myself. I mean, we went to like St. Lawrence Island. We went to Little Diomede, okay? Little Diomede is like next to Russia, you know, like the little thing where the two come together.
Wow.
I mean, that place is like the Rock of Gibraltar. I mean, when you fly in there, you land on the ice. Okay, I mean, this is the runway. Okay, and it's not like flat. It's like, and you taxi up to the village, which is on a rock. And there's like 5 beluga whales laying there on the ice. You know, and some seals. That's the daily catch. Then the guy asks you, he goes, you want to go crabbing? And you go out on the ice and you take a little line and you take a little piece of fish and you put a little weight on it, and you drop it down there. Then you wait and you feel it and then you pull up and you got a big cream crab on it.
Hey, back to I just remembered that the question about the liters, like how many, I still don't have a good idea as to what one of these dwellings, like what is the total volume of water and what's the throughput like? So I think we got distracted by other things, but let's dig into that one.
Okay, now again, all of this comes down to engineering. Okay, so what we've got here, okay, so whatever amount of water you got, I don't care if you got 100 liters or 1,000 liters, okay? So whatever tank or whatever, like for example, my idea would be that every house should have its gutters at the moment, and you should collect as much water as you can. You got a swimming pool, couldn't be better, okay? But if you can collect some water, but even if you had, let's say 500 gallons of water, okay? Now we're gonna put that water into my first primary tank. And so that primary tank is 1,000 liters, which is 250 gallons. I also need my 4 tanks, which are 55 gallons, which is another 250 gallons. So let's say we got 500 gallons. The real output is how many reverse osmosis membranes do you need? I can make as much water as fast as you want with as many membranes as you want. I can make you 100 gallons of water a second if you want. Well, you can use that water and it can come back and I can be making that water just man. So the limiting factor is not the quantity of water, it's the amount of membranes. Okay, so, and the pulp. Okay, so you're gonna have, if you had 20 membranes, you'd probably have to have 3 pumps or 4 pumps, but they're little pumps.
How does the ozone fluctuate relative to the membranes?
The ozone is only used with that initial water. Okay, so the ozone, okay, so let's say that we need 100, let's say we need 1,000 gallons of water every hour. Okay,
Be a lot.
that's a lot of water. Okay. Okay, well, that would probably mean that you'd probably have to have 2 of my systems, maybe 3. Okay. So with the membranes, you could get to a point, okay? I mean, so you could say, well, this pump and 4 of these membranes will make this amount of water for this much money, for this much energy. So instead of having one big one, it's easier to have 1 or 2 or 3. So you have Model A. If we wanted to get into miniature, we'd have like Model B. That would be miniaturized, but you might need 2 or 3 Model Bs, okay? So all of this comes down to, like, my basic idea here is totally adjustable. But you aren't going to ever need a river full of water, okay? The water that you've got, if you design it correctly, you can recycle that water immediately. Okay, so I'm not saying that if you brush your teeth, you're going to drink that water in the next minute. You're going to be able to drink that water tomorrow. Okay, but that water is going to be recirculating and going around.
So that is kind of the question that I'm getting at. It's because depending on the source, you're going to have different timelines for that water coming back to drinking quality. So if it's rainwater, I mean, that's probably good to go. You just send that right through the reverse osmosis filter. But if it's effluent, then that's got to go. It's got to sit. You're going to have to hit that with the ozone. You're going to want that to circulate for a while. So are we, in general, several days? Like, what's the rough analysis on that?
You see, gray water is not that bad. If we get down to my PDU, or the productive dwelling machine, the largest polluter of gray water comes from the kitchen sink. Okay, so remember I told you about the garbage disposal and the way you clean it there? So by reducing the amount of load by the design of the kitchen, in the first place, reduces the amount of time that you're going to have to screw around with trying to clean it up. And so, like I'm saying, the dishes and the grease are the most problematic in gray water. It's not the laundry. Okay, the dirt is no problem. That settles out and is no big deal. It's grease. And that grease comes from the kitchen, okay? The shower is no problem. Brushing your teeth is no problem. Even blood, and mucus is not that big a problem. But it's grease. It is the biggest problem. And that grease, by separating at the kitchen, by having it washed into the composter, is the most important part. Even if you, like my parents were in the restaurant business, if you're familiar with the restaurant business with the large wash things or whatever else that, big dishwasher things, the first thing they have is a big wand that cleans everything and pushes it down a garbage disposal before they load it into the rack and before, okay? Same thing needs to be in the household. This is what I'm saying about the trash compactor, everything. This is where we come back to a better and better idea. Clint doesn't have all the ideas at the moment. He's got the basics. So we're not putting raw sewage into this thing, okay? So we're putting gray water, which is not, from my experience, is not that bad, and can be protected as far as doing it. But so far, if let's say we sold this to a commercial operation, even a good example would be car washes, which already use recycled water. Now, the biggest problem with the car washes is the chemicals that come off of the car, okay, the oils and the gasoline and all that kind of stuff. And all that, again, is being able to be taken out through reverse osmosis. Now, those car washes only use the recycled water and the finished water. Okay, so when it comes off of it, so the basic water the primary can use can be some pretty rough stuff. So any of these things can be cleaned up. And I'm not saying, like what you're saying, how big, how size, whatever else. This is where the new engineering world comes in. Okay, so there is no, as they say, no one size fits all as far as doing it. But the basic whole premise is you start with ozone first. Let the ozone do the magic, okay? Because whatever is in that water, the best animal I can think of attacking it first, which I don't know what's going to happen, but I would set ozone first, okay? After the ozone, then you can go through any kind of filtration. I mean, we use filters that are 0.01 micron. I mean, so you can all kind of filters if you had something that ozone doesn't heat up. Let's say it's plastic, let's say it's some sort of something. Or, so if it goes, and then you can catch it in a filter, if we've got, my filters are here. But anything that's organic, ozone is going to eat it up, and it's going to kill it. Okay, then it's just a matter of pump sizes and flows and storage and whatever. So this water, so when it's running, like in those blue tanks, which it's running right now, those blue tanks are filled with ozone, okay? And whatever is in the water is recirculating around. And if it lived once by going through those 4 tanks, and it's got to go around again, it's got a good chance it ain't going to live again. And if it's dirt and it somehow got through again, it's going to settle out someplace. So the nice thing about having these great big tanks is especially the potential of settling. I mean, settling is one of the biggest things in water. First thing you want to do is let it settle. You know, skim off the top or whatever. And so that's what these tanks do, is they allow a settling, but they allow the killing and the eating up of the majority of the problem. After that, the whole thing is the protection of the membrane. And the biggest, the most difficult, hardest thing is protecting that membrane from bacteria. When the bacteria get on that membrane, they start sliming the membrane. And when it starts sliming, then it decreases the effectiveness, and also it potentially, so you want to do all this work first, okay? And we tried that initially when we did this whole thing. I mean, these guys I worked with reverse osmosis, they looked at me like this, first, like, you are crazy, aren't you? I'm like, well, yeah, well, we'll get over that first. Can you do this? And they said, what do you want to do? I said, this is gray water. I said, I have these tanks, and that's what and this one guy, his name was Joe Thola, never graduated from high school, but his father was in the swimming pool business, and so he learned about water. That guy knew more about water than anything I ever knew, or any engineer I ever met, because he worked with the problem. He understood what was going on, okay? And so when we were doing this thing with ultraviolet, and the initial tank was all slimy, and it was all, it wasn't even gray, it was black, okay? Because during the night, it would just build up, okay, because it was alive, okay? So even an aerobic system is an alive system, okay? So admittedly, it's alive and it's eating up some things, but as it's eating up, it's getting bigger, okay? And eventually you have to clean the damn thing or whatever. Whereas ozone, it ain't getting bigger, it's getting smaller. When we first had Joe brought, we were doing this thing in my basement when I lived in Minnesota. And so he said, well, let's try ozone. He brought this little box, and we plugged it in. I went to bed that night. I came back downstairs the next day. The tank was crystal. I mean, this thing was black when I went to bed, and it was crystal the next morning, okay, just from circulating ozone. That told me everything. But the thing was, then I splashed some water on the damn thing and I broke it. So this is where I learned about again, all of these things. The ozone generators I had, I broke some of these because the check valves didn't work out. As you break something, it costs you $600, $700 to get the damn glass back. That's why these new ozone generators, to me, are invaluable because I've backed up water into them. See, the nice thing about ozone, there's no moving parts, nothing, just strictly this spark.
That's pretty
So
cool.
it is so natural. It is very, very cool.
Clint, this has been an awesome conversation, and I'm wondering, is there any kind of final things or summations that you'd like to communicate? Some of your thoughts here.
Well, number one, I appreciate talking to you. This is very valuable, and I invite you to come to Costa Rica anytime. I'm very fascinated, not only fascinated, but appreciative of the people, especially in Canada. So I worked with Canada people before. I did a system in Whitehorse one time, actually. If there's a possibility that with our communication or with your potential, if somebody from a cooperative can listen or appreciate the potential of finding some financing of this 50 to 100,000 that I'm talking about, to come to Costa Rica and put this together is what we need. I'm seeing that there are other people in the world who need this technology. Okay? And I'm fortunate to be able to, I take a shower with reverse. When you have reverse osmosis water, you don't need as much soap. Okay? So when you have soft water, so all of these things change. Okay? So just, it goes on and on and on and on and on. But the real thing is that I'm not a person who just stands up here and talks about stuff. I've got something you can kick, and that you can taste, and that you can test, and that you can quantify in regards to how much are we talking about. Okay? So I can go head to head with any CEO, any COO, any engineer, any architect, and talk straight talk with them. And if they want to talk straight talk, then we've got an opportunity to work together. We can help humanity in so many ways. This whole thing about war, like Buckminster Fuller said, and we talked about, instead of killing we have living. And it's technology that takes it to change from killing to living. We have the technology.
Well said. Clint, what an absolute pleasure. Again, innovator in the field, futurist, Dymaxion designer. Thank you so much for your time.